Next up, we have Jim Fan. You all know him. Come on up, Jim. Jensen was talking about him just this morning. He is not only director of AI at Nvidia, but also distinguished research scientist, and he'll talk to us about physical AI.
So a couple of days ago, I saw a blog post that caught my attention. It says we passed the Turing test and nobody noticed. Well, Turing test used to be sacred, right? It's the holy grail of computer science, right? The idea that you can't tell the difference between a conversation from a human or from a machine. And then it just so happens that we got there. We just got there. And people are upset when O3 Mini took a few more seconds to think, or that Claude is not able to debug your nasty, nasty code, right? And then we shrug off every LLM breakthrough as just yet another Tuesday. You guys in the room are the hardest crowd to impress. So I would like to propose something very simple called the Physical Turing Test. And the idea is like this, right? You host a hackathon party on a Sunday night, and this is what you end up with. Your partner's yelling at you, and you're like, damn, on Monday morning, I want to tell someone to clean up this mess and make me a very nice candlelit dinner so my partner can be happy. And then you come home to this, and you cannot tell if this was from a human or from a machine's work, right? Simple enough, the Physical Turing Test. But where are we now? Are we getting close? Well, look at this humanoid robot getting ready for work. It didn't make it, right? And how about our dogs and the banana peel? Yeah, and the robot instruct, to make you a breakfast cereal. Well, it correctly identifies the milk. I will give that an A-, right? It's well-intentioned. Oh, it spoon feeds you. It's a VIP experience, right? Look at that. I'm jealous. I got no one to spoon feed me. Yeah, this is where we're at. So why is it so damn hard to solve the Physical Turing Test? You guys know that LLM researchers complain a lot, right? They complain a lot. And recently, some guy named Ilya, he complained. He said the LLM pre-training is running out of data. And he even called the internet the fossil fuel of AI. And he said, we're running out of data to train LLM. Well, just spend one day with roboticists, and you'll know that how spoiled the LLM researchers are. We don't even get the fossil fuel. So this is a data collection session at Nvidia headquarters. There's a cafe in Nvidia, and we have these humanoid robots set up where we operate them and collect the data. And this is what the data look like, right? The robot joint control signals. And these are continuous values over time, and you cannot scrape this from the internet. You can't find it on Wikipedia, on YouTube, on Reddit, anywhere. So you have to collect it yourself. And how do we collect it? We have a very sophisticated way, but also very expensive way, called teleoperation, where you can have a human wear something of a VR headset that recognizes your hand pose and streams to the robot. And in this way, you can teach the robot what to do, like pick up a bread out of a toaster and then pour honey over it. But you can imagine this is a very slow and painful process, right? So if you put it on the scaling plot, basically it doesn't scale at all. The real robot data is the human fuel. It's worse than the fossil fuel. You're burning human fuel, and what's worse, it's at most 24 hours per robot per day. And in fact, you will get much less than that because the human gets tired and the robots get tired even more than the humans. So this is what you get. And what to do, right? How to break this barrier. Where is the nuclear energy for robotics? We got to have clean energy. Can't live on fossil fuel forever. Well, enter simulation. We got to leave the physical world and then do something in simulation. So we trained this robot hand to do superhuman dexterous tasks like spin in a pen in a simulation. And well, it's superhuman with respect to me because I couldn't spin pen, and I just gave up a long time ago in childhood. And I'm glad that my robot, at least in simulation, can do it better than I do. So how do we train the hand to do a sophisticated task like this? There are two ideas. One is you got to simulate at 10,000 times faster than real time. meaning that you should have 10,000 environments running in parallel on a single GPU doing physics simulation. That's number one. And number two, the 10,000 copies of the environment cannot all be identical. You got to vary some parameters like gravity, friction, and weight, and we call that domain randomization. And that gives us the simulation principle, right? Why does it work? So imagine if a neural net is able to control the robot to solve 1 million different worlds, then it may very well solve the 1,000,001st world, which is our physical reality. So in other words, our physical world is in distribution of this training. And then how we apply this? You can build a digital twin, right? A one-to-one copy of the robot and the world, and then you train in simulation, you test it on the real world. Directly transfers, right? Zero shot. And you can do a hand, and this is the most impressive task that we could do. So basically, you have a robot dog on a ball, and then we transfer that to real world. This is at UPenn, and basically someone walking the robot dog, our researcher, super weird, looks like a Black Mirror episode. And this is called Dr. Eureka. Actually, like one of the researchers tried his dog on the yoga ball. At least we're super dog dexterity right now. Yeah, the dog cannot do it. Right? And next, we can also apply that to much more complicated robots like the humanoid. And these humanoid robots, they went through 10 years worth of training in only 2 hours of simulation time to learn walking. And then you can transfer that. And it doesn't matter what the embodiment is. As long as you have the robot model, you simulate it, and you can do the walking. And can we do more than walking, right? So as we are controlling our body, you can track any pose that you want, track any key point, follow any velocity vector that you want. And this is called the whole body control problem of humanoid. And it's really difficult, but we can train that, right, on 10,000 simulations running in parallel, and we can transfer that zero shot without any fine tuning to the real robot. So this is at the Nvidia lab. We actually need to slow down the video. So the first video is in real time, and the next video is slowed down. So you can see the sophistication of the motion that it does. It imitates the human, all these agile motions, while standing balanced. And guess how big of the neural network it is required to do this? It is 1.5 million parameters, not billion, 1.5 million parameters is enough to capture the subconscious processing of the human body, the system one reasoning. 1.5 million parameters. So if we put this on this diagram where you have the speed versus the diversity of the simulation, I think we'll call this simulation 1.0, the digital twin paradigm, where it is a classical vectorized physics engine, and then you can run that to 10,000 up to 1 million frames per second. But the issue is you gotta build a digital twin. You need someone to build a robot, to build the environment and everything, right? That's very tedious and manual. So can we start generating parts of the simulation? All of these 3D assets are generated by a 3D generative model. All of these textures from Stable Diffusion, or any diffusion you would like. All of these layouts generated by prompting an LLM to write XML. And putting all of these together, we built a framework called RoboCasa, which is a large-scale simulation, a compositional simulation of everyday tasks. And everything here, right, except the robot, everything is generated. You can compose different scenes, but it still relies on this classical engine to run, but you can already get a lot of tasks from it. So now what we can do is we can have a human, again, do the tally-up, but this time, you tally-up in simulation. You don't tally-up a real robot. You tally-up in simulation. You replay that trajectory in simulation, and you add all the great hardware-accelerated ray tracing to make these beautiful scenes with lighting, and you can even vary the motion, right? If you tele-operate and then move the cup from here to here, you don't have to demonstrate moving cup from here to here or from here to here again. And then, putting all of these, you have one human demonstration in the simulation. Through environment generation, you can multiply that to n, and through motion generation, m times n. And I promise you, this is the only math that you're going to do today. That's how we multiply the data. And then you put it together. Column 1 and 3 are the real videos from our real robot. And column 2 to 4 are from the RoboCasa simulation, all generated. So you can still tell that these textures are not real, but they're kind of close enough. And what do we call the things that are close enough? We call it the paradigm of the digital cousin, It's not a digital twin, but it kind of captures, right? So a digital cousin. And these simulations run slower, but they are this kind of hybrid generative physics engine where we generate parts of it and then delegate the rest to the classical graphics pipeline. Now, simulate this scene, right? You got soft body, you got fluid, you got everything. It's gonna take a very long time for artists or a graphics engineer to simulate this scene properly. So if we look at how graphics evolved, it took 30 years to go from the left to the right. And it just took video generative models 1 year to go from left to the right, simulating all the deformable, right, noodles, right? It lost some sense of humor here, but that's a price I'm willing to pay for latest Sora, VO, right, all these generative models. Only 1 year, and that's the power of scaling and data-driven process. Do you recall this video I showed at the beginning? I tricked you guys. There's not a real pixel in this video. It is fully generated by a custom model. So what we do is we take a general purpose, open source, right, state-of-the-art video generation model, and we fine-tune it on domain data collected in our real robot lab. And all of these are generated. And now you can prompt the model to imagine different futures, right, to simulate the counterfactuals. So you see these two frames are the exact same, but given different language, the generated video is actually going to follow language and do the right thing, even though this motion never happened in the real world. And then you can do this. The video diffusion model doesn't care how complex the scene is, right? It doesn't care if there is like fluid or soft body. And the same scene, you can ask it to pick up different things. It will actually use the right hand to grab the object and put it in the basket. And these are all generated. All of these are generated. None of a pixel is real. It gets all these kind of reflection correct, right? All of those interactions correct. And one of my favorite is the robot playing ukulele over there. So basically, the video model probably has seen millions of humans, like lots of humans playing ukulele. And then it just simulates the robot finger to do that. Even though the hardware doesn't actually support it, the video generation model can do it. So if we put this in perspective, right, this is simulation 2.0, where it's got a lot of diversity, but it could run pretty slow these days. And nobody calls it, but I'm calling it the digital nomad, right, which is wandering into the dream space of a video diffusion model. And what is a video diffusion model? Right? It is a compression of hundreds of millions of internet videos into this kind of simulation of the multiverse. So just like Doctor Strange, right? You instantiate the robot in the dream space, and basically the robot can now interact with objects everywhere, everything everywhere, all at once. So you have this embodied scaling law. Okay, so Jensen left, but I think he's gonna like this a lot, right? So you need a lot of compute, to scale up the classical simulation, and that's the Sim 1.x series. The issue is, as you scale this up, it's gonna hit a wall because the diversity is limited in this handcrafted system. And then this is the neural world models, the Sim 2.0, that's gonna scale exponentially with compute. And that's a point where the neural network outperforms a classical graphics engineer. And together, these two adding up, that will be our nuclear power to scale up the next generation of robotics systems. The more you buy, the more you save. So at the beginning, whoever says that the compute situation is going to improve, not worse, burn this figure into a retina and think again. And you put all those data into what we call vision language action model that takes in pixels and instruction and output motor control. And you get what we open sourced at March GTC, Jensen's keynote, called the GR00T N1 model. And we run on the robot. It could be romantic sometimes. Yeah, you can't imagine how much cleaning we did during training. So yeah, it's able to grasp the champagne. In this one, it did it perfectly. Yeah, did it very well. And then it can also do some industrial tasks, pick up some of the factory objects, and it can also do multi-robot coordination. So GR00T N1 is fully open source. And actually, the future series of the model will also be open source because we're following Jensen's paradigm of open source and democratizing physical AI. Great, so what's next? Where do we go after we solve physical AI? I will say the next thing is the physical API. Throughout human history, right, 5,000 years, we have much better tools, right, much better society in general, but the way we make dinner and do a lot of hand labor are still more or less the same, right, from the Egyptian times. And maybe for 99% of the human history, we have this structure where you go from raw materials through human labor and you build civilization. And maybe in the last 1% or like 50 years, we have human labor shrinking, and we have these highly specialized, highly sophisticated robot systems that can do one thing at a time, and it's very expensive to program, but they still live our society. And that's what we have right now. And this is the future, is to push that blue bar all over the place, all over there, and have the physical API, right, just like LLM API, moving around chunks of digits, of bits. The physical API moves around chunks of atoms. You basically give your software a physical actuator to change, right, the physical world. And on top of this physical API, there's going to be a new economy, a new paradigm, where you have physical prompting, right? How do you instruct these robots? How do you teach them? Language sometimes not enough. You can have physical app store and skill economy. So let's say a Michelin chef doesn't need to just go to the kitchen every day. He can teach a robot and then basically deliver a Michelin dinner as a service. And I should quote Jensen here again. That future, everything that moves will be autonomous. And one day you'll come home, right, to a clean sofa and a candlelit dinner, and your partner's smiling at you instead of yelling at you for not doing the dirty laundry. That still motivates me every day, right? And you bought 2 humanoid robots last month. It's running Groot N7, and those robots just fade into the background, right? Kind of like an ambient intelligence. It fades into the background. And you wouldn't even notice the moment that we pass the physical Turing test. And that day will simply be remembered as another Tuesday. Thanks.